Hi and Assalamualaikum. My name is mem561 and today I want to present to you all about half and shaft assembly. Let's go. Okay, first thing first, we talk about the abstract. The case study focuses on designing and analyzing a critical mechanical component for high precision and smooth operation in automotive or aerospace application. Firstly, emphasis is placed on the importance of fit and tolerance, exploring types like clearance, transition, and interference, and determining the best class of fit. Next, geometric dimensioning and tolerance GD&T is highlighted. The manufacturing process is analyzed considering both traditional methods, machining, casting, and non-traditional approaches, additive manufacturing. After that, the selected process is evaluated for precision, cost effectiveness, and feasibility with attention to tools and materials needed to meet industry standards. If joining processes are required, techniques like welding, brazing, or adhesive bonding are outlined along with their advantage and equipment for high precision assembly. Last but not least, the case study concludes by summarizing the design decision, manufacturing technique, and fit and tolerance analysis, emphasize the importance of precision and quality to meet the demands of automotive and aerospace industry. Okay, next we move to the introduction. So as we can see, the purpose and functionality, the hub and shaft of the flange coupling connects two rotating shafts, ensuring alignment, stability, and smooth power transmission, making it essential for high-performance automotive and aerospace applications. Next, for the precision in design. High precision in design allows the hub and shaft to withstand dynamic loads, vibrations, and challenging operating conditions. Proper fits, tolerance, keyways, and splines improve assembly and prevent slippage or misalignment. For the assembly technique, the flanges are securely joined using bolts and nuts, tightened uniformly to avoid stress concentration. Additional techniques like welding, adhesive bonding, or sealing may be applied to enhance durability and performance in critical conditions. And for manufacturing and inspection, processes like machining, surface finishing, and quality inspection ensure the hub and shaft meet stringent industrial standards for accuracy and durability. And then we continue to the material selection. Common materials include carbon steel for strength and cost effectiveness, stainless steel for corrosion resistant in harsh environments, cast iron for wear resistant and affordability, and titanium for its high strength to weight ratio in advanced aerospace applications. And lastly, preferred material. Stainless steel is suitable is chosen for its strength, corrosion resistant, and machinability, making it ideal for flange in harsh conditions and high load application, ensuring longevity, reliability, and dimensional precision. Okay, so for fits and tolerance, as we discussed in our report, we know that types of fit, there are some types of fit. So first thing first is clearance fit. Hole is always larger than the shaft, ensuring free movement. For the subtypes, loose running fit, maximum clearance for free movement even with misalignment or contamination. Close running fit, reduced clearance for control motion under moderate speeds or loads. And for free running fit, balance between clearance and friction used in shaft with bearings. And sliding fit, minimal clearance for precise play free movement, like example, slideway. And for location fit, tight fit for stability with minimal clearance, ideal for precise assembly. Okay, we move to the transition fit. Tolerance zone of the hole and shaft touch or overlap. For the subtypes, we see the similar fit allows small clearance or slight interference suitable for light loads and occasional separation. And for the fixed fit, provide a more secure joint with negligible clearance used for permanent or semi-permanent assembly. And lastly, for interference fit, the shaft is larger than the hole, creating negative clearance. For the subtypes, press fit, moderate interference requiring a press assembly used for mounting gears, bearing, and flange coupling. Driving fit, higher interference requiring more for assembly, suitable for heavy machinery. And for force fit, largest interference requiring heavy force or heat shrinking, used in permanent critical assembly like axles or wheels. So as we can see, the hub and shaft design, interference is used interference fit is used in the assembly of the hub and shaft. Two parts fit tightly together when assembled and that much force or special tools are required. Typical fit standard, we use the hub, hole basis, H7, P6, and for shaft basis, we use P7, H6. Okay, now we jump to the engineering drawing. So this is our drawing that we made using a katia that is flange left part. So we make it one by one part and then we assemble it together. Okay. Okay. So this is our drawing in katia for the shaft part. So basically the shaft part will fit in the hub. Okay. So lastly, this is drawing in katia for the assembly of flange coupling. So basically the assembly is combined with the shaft, the hub part, the flange part, and some nuts and bolts. That's all. Okay, now we move to the geometric dimensioning and tolerance, GD&T. So this, as we can see, this is our drafting in Katia for flange left part. Okay, as we can see that we found the tolerance based on the shaft and hole and shaft based on the table. La for the whole H for the hub part we use the H7 P6 tolerance and we use the diameter 50 diameter or less and then we can see we take that the 0.0025 and 0 from there. And now this is the drafting in Katia for the shaft part. As we can see, we there are also a tolerance we found at the table P7H6 uh, using the same diameter 50 diameter or less and we found that the tolerance is 0 and 0.0016. Okay. Manufacturing process for non-traditional process. The objective of non-traditional machine overcome the limitation of conventional methods using energy, which is mechanical, thermal, electrical, or chemical, rather than sharp cutting tools. The advantage of non-traditional process is ideal for hard, brittle, and poorly machinable material. Achieve high precision, stress-free machining, and complex geometry. Widely applied in aerospace, electronic, and biomedical industries. The process is for non-traditional process is first EDM, electrical discharge machining. It is suitable for hard electrically or conductive materials, offer exceptional precision, intricate machining, and stress-free operation. Disadvantage is low material weight and limited to conductive materials. Next, ECM, electrochemical machining, produce burr-free, stress-free finisher for conductive material. Next, USM, ultrasonic machining, non-thermal process for brittle material like ceramic and carbide. Next, LBM or EBM, which is laser or electron beam machining. LBM versatile for various materials of thin or intricate pattern, and EBM micromachining and high aspect ratio cut. And lastly, hub and shaft component, we prefer EDM. EDM can handle hard material and achieve high accuracy, produce intricate features with tight tolerance critical for flange softening, and ensure proper fit alignment and stress-free machining. Limitation of conventional machining is challenge require tool in around 30 to 50% harder than the workpiece, limiting machinability for hard material. It is difficult to create micro-scale features or complex geometries, and brittle material crack under mechanical stress, making them unsuitable for cutting. The comparison is convection machining faster and cost-effective for simple design and soft materials, but limited in precision and material versatility. ADM advantage: machinists are brittle materials without machinal force, achieve intricate geometries and tight tolerance, minimize distortion, ensuring alignment and durability of components, and limitation of ADM is lower material removal rate, limited to conductive material, and precast layer require additional finishing. Advantage and disadvantage of process. Conventional machining. Advantage: widely available, cost-effective, and modern efficient. Disadvantage: challenge hard material for complex shape. Casting. Advantage: cost-effective for large volume, near net shape. Disadvantage: poor dimensional accuracy, secondary machining need. Additive manufacturing. Advantage is complex geometries, minimum material, quick prototyping. Disadvantage is limited material option, slower for large parts, potential surface finish issue. Laser cutting. Advantage: high precision for thin or flat components, thin edge, and formation. Disadvantage is limited to 2D profile, less effective for thick material or thin shape. For instance, advantage is highest precision for intricate profile, tight tolerance. Stress-free machining ensure dimensional integrity and excellent surface finishes, reducing post-processing. The disadvantage is low material converted to productive material. Next, we proceed to joining process. For hub and shaft assembly preparation, use compatible material for the hub and shaft. Clean or frying surface to remove contaminants such as oil, rust, or dirt. Design joint directly to achieve mechanical requirements, ensuring proper load transmission. Precision tool and fixtures or clamp are used for alignment positioning. Joining method we use we- joining method as visual welding method like MA apply it to weld and join the hub and shaft. Friction welding (FRW) generated through rotational friction followed by axial pressure for strong seam joint without melting metal. Brazing millimeter with a long melting point, melted and distributed via capillary action, ensuring minimum heat affected zone and proper alignment. Post-joining operation: pull the joint naturally to minimize residual stress. Inspect the joint using non-destructive testing, which is additive method to detect defects. Links like a plug or residue for a smooth finish. Perform finishing operation to enhance performance and protect against wear or corrosion. And the final step is inspect for alignment and functional testing under simulated operating conditions. Ensure compliance with design specification before integrating into range of link. Particular joining process factor for selecting a process. Applications, mechanical requirements, material properties such as weldability or dissimilar materials, operational environment, and production efficiency. Joining method A. Welding, which is strong permanent point joint for high strength application. Visual welding, such as PTM, SM for weldable material. Friction welding, FW, for defect-free joint with minimal heat affected zone. The advantage is eliminates hardware and provide robust connection. Brace, suitable for materials with poor weldability or heat sensitivity. Create precise uniform joint with fatigue and corrosion resistance. The disadvantage is lower strength compared to welding, unsuitable for heavy duty application. Adhesive bonding, useful for weight reduction, vibration damping, or heat sensitive materials. The limitation is lower mechanical strength, not suitable for high load application. So, preferred process is welding is more suitable for flare stocking due to its strength and durability. Pressure welding are the disadvantages of defect-free joint millimeter. Brazing is an alternative for moderate material. Adhesive bonding is not ideal for high stress strain coupling. Equipment and technique of joining process. Firstly, user welding. The AG will be able to clean defect-free weld precise heat control, ideal for thin material and space components. Electron weld leads SL offer deep, narrow weld with minimal distortion and suitability for tight tolerance and dissimilar metals. Solid-state friction welding FRW generates heat through friction and applied pressure, ideal for high-stress components like shaft. Ultrasonic welding, suitable for bonding thin sheet
wire or composite using high frequency vibration. Diffusion welding create precise joint in high performance material atomic diffusion under heat and pressure. Brazing suitable for dissimilar or heat sensitive materials, especially in non-critical aerospace applications. Adhesive bonding offer vibration damping protection but is limited to non-barium applications. Preferred technique for aerospace applications is CIG, electron beam welding and friction welding for precise strength and reliability. Brazing and adhesive bonding is less demanding application. Next, we move to discussion. First, for tooling material selection or milling is firstly high-speed steel (HSS). The advantage is affordable, resistant to chipping, ideal for softer materials such as low-carbon steel and aluminum. The limitation is lower wear resistance and heat tolerance compared to advanced materials. Carbide fluid. Advantage: high speed precision, excellent wear resistance, high heat tolerance and long-lasting sharpness. Application suitable for harder materials such as alloy stainless steel. Limitation: expensive and brittle, require careful handling. Next is thermal tool, which is ceramic metal composite. Advantage is fine surface finishes, high speed machining, superior heat resistance and chemical stability. The application is best for medium hard materials such as cast iron and hard stainless steel, but limitation is limited toughness, which is sensitive to shock and vibration. Next, coated tools, which is coating titanium nitride (TiN), titanium oxide (TiN), or diamond carbon (DLC). Advantage is enhanced wear resistance, reduced friction, improved heat dissipation. The application is ideal for high wear operation or dry. Limitation is higher cost compared to uncoated tool. And lastly, polycrystalline diamond (PCD). The advantage is hardness and most wear-resistant option, excellent for non-ferrous material like aluminum alloys. The application is lightweight up and shaft design requiring exceptional surface finishes. The limitation is unsuitable for ferrous material to chemical reaction at high temperature. Next, tool types for milling operation. Hand mill. Versatile, used for contouring, slotting, and pocketing operations. Press mill, best for machining large, flat surface, ensure excellent surface finish and dimensional accuracy. Slotting cutter, used to create keyword or slot in shaft assemblies. T-slot cutter, employed for producing T-slot in hub assemblies. Thread mills, essential for machining plate, often required for flash connection. We can conclude that optimized tooling selection, the selection of tool types such as hand mills, press mills, floating cutter, and thread mills, ensure that the specific machining needs of hub and shaft assemblies are met. Prioritize cost effectiveness. High speed steel HSS provide a cost effective option for general purpose machining. Enhance performance. Carbide tools offer high speed precision for harder materials. Advanced materials like granite and polycrystalline diamond (PCD) are ideal for achieving superior surface finishes and machining non-ferrous materials. Coated tools further enhance performance by improving resistance and heat dissipation. Okay, thank you.